So, welcome everybody to Lecture 4, Databases and Information Systems in the winter semester 25-26. Lecture today is about query planning, basics. I will talk about your experiences with exercise sheet 3, which was about database design, so a very gentle start to the topic of databases. This is a reminder to please tell your tutor, for those of you who do the sheets, to which kind and extent of feedback you want. I think most of you said it the first time, but then didn't say it again. This might change over the course of the semester, so just say it every time. And if it doesn't change, just copy and paste from your last sheet. That's what the tutors sent back to us, that they want to know this every week. So please do it. Thank you. So contents today is last lecture was very informal, very gentle introduction to databases. This lecture we will make it a bit more formal, but it's still very gentle, and you will see what it's about. It's query planning, finding the optimal sequence, and so on. This will become clear. And the last lecture was really playing around, gather a bit of data, make your database tables. Now you start writing your own database engine, so your own little SQLite 3, and I think this will be very interesting. And I highly, highly recommend to do this exercise, and I will say something again at the end. But let me just say it again now. This lecture on the abstract level, it's not so hard to understand. Okay, there's a lot of noise here, so let's just wait for 10 seconds before the front row sits down. I will say that again at the end, but let me say it again now. Understanding this conceptually today is, I think, not so hard, but then turning it into code is not so easy, and you only learn that when you do the exercise sheet. If you don't do it now, you will have to do it in the preparation for the exam, because the exam will ask programming questions. So please consider doing this exercise sheet. And of course, it should be exercise sheet 4, not 3, because 3 we had. Let's go on. So, exercise sheet 3, experiences. Loved the lecture. It made me immediately want to start doing the exercise sheet. That's perfect. That's the main purpose of the lecture. Was relatively easy, but still took some time. Fun exercise, nice way to introduce DB design and queries. Very good learning experience and helped me to get used to SQL. That was exactly the task of the first lecture about databases, so I'm happy to hear that. It took a while to get the data sorted into different tables. A lot of you said that. So the first part, gathering the data and putting it into tables, was hard, but it was a satisfying process. Lecture gave a good introduction. The lecture nicely refreshed my knowledge on databases. Since I had some SQL back in school, it was pretty easy. Several of you said that they have learned this stuff before in a previous life, but it was a good refresher. Useful exercise, even though creating the tables was annoying. A lot of you said that it was a lot of work to gather the data, but of course, even in research, that's a very significant part of the work. I mean, in this lecture, we often give you super nice data, and Robin or myself do all the work, but this is an important part of research, gathering the data. Everybody basically said it was a significant amount of work. Some liked it, some found it annoying, so you should learn to love that part, because it's just an essential part. Exhausting, but very rewarding at the end when it all worked. And then there was this guy, Richard Hipp, who was the creator of SQLite, so we dabbled a little bit into that. SQLite, in case you didn't know, is the most used database in the world with trillions of installations. Every phone has it, every car has it, running on washing machines, on everything. And it's essentially the work of a very, very small group. And if you boil it down even more, it's essentially the work of this guy, Richard Hipp, and he's a very special guy. And so one question was, what struck you most when you... So I highly recommend reading a little bit about him. His website, it looks like SQLite fields. Yeah, so it's a very old-fashioned website. This guy had no idea what he was doing half of the time. It's crazy how good his product was, that big companies were just offering him opportunities, and he just went with the flow. It's really quite interesting because he wasn't, I'm not sure he studied electrical engineering, but it's not that he was a computer scientist by training. So actually he had to look up stuff. How do you do a join? How do you intersect two sorted lists? It was not someone who was super familiar with this by training, but he actually looked it up in textbooks. So it's funny, and then it's a product that's used so much. That's also something that struck me when I first read it. MCDC test coverage. You write unit tests, and I hope you have learned and appreciated by now how important unit tests are. But there's a different industry standard, which is about tests so that each branch at the machine code level, whenever you have machine code instruction that says, depending on the value of this register, jump there or continue with the next instruction, and each such branch you have to test both outcomes. And when you do that, then you're essentially bug-free. And at some point, SQLite did that, and it took him a year, full working day every day to solve this. It was very exhausting. And after that, they essentially had no more bugs. Billions of unit tests, so for the exercise sheets you have 3 or 4 billions, and they run for 3 days prior to each release. They run on all kinds of machines, operating system, architectures, including very, very old architectures. Because when you have something like this that's used a lot, then people use it on machines from the 80s. Yeah, and that's also funny, so it's interesting that you found out all of this. SQLite basically has no dependencies on other stuff. This guy said, let me write this from scratch. He even wrote his own parser. He even wrote his own version control system. He said, SVN, nope, git, nope. I will write everything myself. It's actually something we also do in our own research. I showed you our own system for database system. We will talk more about it later in the lecture. We also like to do things from scratch, but this guy took it even further, like he trusted Noah. He writes I think it's taking it a bit too far. You don't need to write your own version control systems. Yeah, but that's what he did. Okay. And basic, is there something I wanted to show here? No, maybe later. Let's start with today's contents, basic operations. So a bit of recap from the last lecture. So in lecture 3, you saw these select from where queries, and so you learned a little bit about SQL. You essentially learned it by doing, and it was select from where. And the nice thing about these queries is that you could essentially read them like text. So the big question for today and also for the next lecture and even for the one after that is you have a query, what does the database system actually do with it? And in a nutshell, what it does is it implements operations on tables. We will see in a minute what that means. And so 3 operations today, more in the next lecture. And this is actually your task, implementing these low-level database operations. Then you have to translate your query. The query is essentially like a question. This is what I want. Now you have to translate it to a program for your database. And this is called query planning because it's not a one-to-one thing. For one question, you have many ways to execute it. And we will see what that means. And then you actually have to execute it. So you have the query, then you have to plan, you have to translate it to a program for your system, and then you have to process it. And these last 2 things is what you do for the exercise sheet. And again, I highly, highly recommend it. So we will start with the simplest operations which you need to process any meaningful query, and that's projection, selection, and Cartesian product. Will be very clear very quickly what that means, and we already saw them in the last lecture. And by the way, Cartesian product and cross product, we use them synonymously. And the input, each of these operations gets a table or two tables and produces another table. So that's what database systems do. They process tables. You have your input tables, you take two of them, you somehow do something with them, you get another table, you do something with them together with another table. The output is also a table. So database systems are table processing machines, and you just transform the tables on the way. And just because everything is about tables, let's just recap the definition of a table. That's just from the last lecture. I mean, a table is what you imagine a table to be, a little bit more formal. You have the column names, that's just the headings, right? And you have k of them. And for our purposes, these are always fixed. And these are just the headings. You have the domains, where they come from. So maybe it's an integer, a text, so one column has integers, one has text, one has dates. And then you have the rows, and the rows we said are multi-sets of tuples. The R is because we call it rows, and each of them has to be from that domain. We have seen lots and lots of examples about that in the last lecture. We will see more examples today. And just this multi-set thing means you can have the exact same rows twice. So that's why it's a multi-set. Set, because order doesn't matter. You always write a table in some order, but the order has no semantics. You could write it in a different order, it's the same table, and you can have the same row, the exact same row twice, and then it's a different table. It matters whether you have it once, twice, or three times. That's multi-set. And R because rows. Some more basic notation. So if we have two rows, and this is a row is a tuple, so we have one row with n columns and another row with m columns, and now you just put the rows side by side. We will see that a lot. We call that concatenation. So yeah, you have 3 columns, 2 columns, you put them side by side, you have 5 columns. This is easy, I just want to introduce the notation. And if you have a row, so here you have a row with k columns, and you just want one value, the jth value, you just write it like array notation, row, square brackets j, it gives you the jth column. And just for simplicity, we don't start 0 based, we start 1 based. So it's r square brackets 1 gives you the first column, r square brackets k gives you the kth column. And you just ask if there's any. This is just very quick, basic stuff. And let's start with our first operation now. Let's make it a little bit more formal. And this is called projection. And what it takes is a table, a subset of the columns. So this is an arbitrary table with k columns. This is a subset of the columns. And how do we do that? It's just the indices from 1 to k. We will see an example. And then distinct, which is either true or false. You will see an example in a second. And this here, in classical database theory, this is called, okay, that's the wrong. This here is the capital Greek letter pi. Yeah, there's a pi in lowercase and uppercase. That's the uppercase pi. That's just traditional how you call project, but we will just write project. It's not important, just in case you read some literature. So when you do that, why is it called project? Now you just, it just means I have a table and I want certain columns only. So it's, yeah. You just have those columns which you selected. There will be an example in a second. They have the domains from the original table. And now you just have, for each row, you just take the selected columns. And now, depending on distinct true or not, you remove the duplicates or not. Let's just see an example for that. So here we have a table. So finally some examples. So it's you have some. Yeah, it's just 4 people. Anne Hathaway, we learned that. very important trivia that she existed twice. There's the contemporary actress and the wife of William Shakespeare. These are the Wikidata IDs, could be any IDs. So two people with the same name, but they are different people. River Phoenix, Joaquin Phoenix. We just did that so that we have some duplicate entries here. And now just get used to the notation, and you will need that for the exercise sheet. We take this table as input, so this table is called people, it's a toy table here. We want columns 2 and 3. Let me just, so these are just my columns, that's 1, 2, 3. So it means I just want columns 2 and 3, and true means I want distinctness. Vielen Dank, Frank. Distinctness, and what does it mean? Oh, so how much columns, how much rows will the result have if I do that? How many rows and how many columns?
3 rows, 2 columns.
3 rows, 2 columns. Why 3 rows and not 4?
Because it's distinct. The first 2 rows are the same, so they
Yes, the first 2 rows are the same. So this is why you have the distinct here. Here they are not the same, right? But by selecting only certain subcolumns, only first and last, the 2 Anne Hathaways now become the same. So 2, 3, it's just these 2, and then, so simple to understand. And you can say, do I want distinct or not? That's one operation, and you have to implement that. You can. Here's one important thing, and I will say it again at the very end. Implementing this conceptually, it's easy, right? I mean, what do you have to do? You implement project, you just go over these things, you have given which columns you want. I mean, this is not very complicated code, but the whole code design, how you do these operations, will not be easy to understand, how this all fits together. As usual, we give you a template and you have to understand this. So the exercise, and it's really important, listen to this, it has 2 parts. One is implementing the stuff, but then understanding the code design. That's half of the exercise sheet, and it's the harder half. And you absolutely only learn this by doing it. I highly, highly recommend doing the sheet. Otherwise, you only understand it in the abstract. And here I just explain it in the abstract with an example. Next one. So that's projection. So projection is, you have a table, just give me certain columns, distinct or not. The next one is selection. And it's very confusing. You might see that already now. It's called project, but this is actually the select part of the SQL query, right? When you say select distinct first last, you are selecting certain columns, you say distinct or not. This is classically the database operation project. So what you write in the select clause is project. But there's also an operation called select, which is not what you write in the select clause. It's not my invention, but these are just standard terminologies. So select is also simple. You have a table, and now you have a predicate that you can evaluate on each, and this I wanted to, let me just change that. This here I changed that to true and false. I wrote this in funny symbols before, but it was very confusing because the classical true looks like a T. So that's why I changed this too, but let me just make it true and false here. Yeah. So you have a predicate. The predicate is just a function which you can apply to each row and say included or not included. Very simple. This is really just formalism, but still it's important to understand the formalism. And so the result is just a table with the same number of columns, the same domains, but a subset of the rows. And it's just those rows for which the predicate is just a function which you can evaluate on each row is true, right? So project is select columns, select is select a subset of the rows. Could be all rows, could be no rows. Yeah. So this is what I just said. This is traditionally called select, but it's not what you write in the select clause. It's confusing, but that's how it is. Again, project selects columns, select rows. More meaningful way would what names would be select columns, select names. Here's an example. Yeah, so so this is it's the same table now. Our select query is everything from people where first is equal to n. So somebody else, how many rows and how many columns will the result have? Now, yes?
This time it has to be 3 and 3, like all the columns, like ID first and last.
So all columns, that's correct. How many rows?
Sorry, then only 2. Like
2 rows.
I included the header, sorry.
Yes,
It's only 2.
exactly. So yeah, the header is just for illustration, exactly. So 4 rows and 2 rows are selected, exactly, and it's these 2 rows. Yeah, and you already see here in the previous example, this is essentially query planning. So from the query, this is the operation you have to do. This operation implements this query, right? You say what you want, and the database system somehow has to come up with this. Yes, please? So
we should change the double quotes to single quotes in order to do
oh, this, yeah. Here or, okay, maybe it's
maybe
yeah, and the SQL, yeah, that's, okay, and my PowerPoint does autocorrection. So these are single quotes, otherwise it will not work. Yeah, many systems just, and this is just our own notation. We can have double quotes here. Yes. So that's it. And now the other one is Cartesian product. So they should all look familiar from the last time. Cartesian product takes 2 tables, and now you get a table with all combinations of rows, right? So the columns is just, if you have 3 columns here and 5 here, now you have 8. The domains are just the domains. And now the rows are all combinations of rows where one is from the first table, the other is from the other. And this we have already seen in the last lecture. Now we just make it more formal. This is a database operation. And let's just look at an example. And I just take 2 random. So here I have 2 tables. So one is genders. Let's simplify and take 3 genders, female, male, other. These are the Wikidata IDs. And this is not political spectrum. This is just, I wanted to take something super binary, even that's not binary, left-handed and right-handed, so lefty, righty. I mean, it's also used for political stuff. I think the political stuff, is that correct, came from French Revolution, right? I think there in the parliament you had certain people sitting on the right, left. That's where this comes from. Yeah, and when you sit down in a big room, it's also, you sit on the left or the right or in the middle. But so we have 2 hands, so left-handed, right-handed. They're also Wikidata entities. They're Wikidata entities for everything. So, and now we have 3 genders, 2 kinds of handedness. And now you tell me the Cartesian product of the 2, how many rows and how many columns, the way we defined it. And somebody else who has not. The result will have how many rows and how many columns? So it's now all yes? 4 columns and 6 rows. That's correct. Yeah, all combinations, 3 times 2, it's 6, and 4 columns. And yeah, so it doesn't even matter whether the tables have something to do with each other, it's just all combinations. So here it's no a coincidence that here I have this repeated twice, right? I have it repeated twice because there are 2-handedness, and here this I have repeated 3 times for each of the genders over here. So these are our 3 operations. Any questions about this so far? These are our 3 operations for today, yes?
Do you know why it came to be that select is project and project is where and so on?
Yeah, maybe you can research it. I don't know. I think, actually, so this is called relational algebra. So this is like database theory, these operations. And maybe this predated SQL. So maybe before you had a language SQL, I think it took a time for this standard query language to emerge. And before that, you had this theory of tables manipulating tables via operations. I'm not sure, but it's if you find a good answer, tell me. So now we have seen it for each example, right? You have SQL query, you translate it into, and here we didn't translate it yet into a sequence operation, but one operation. Queries can be complex, and now it becomes sequences of operations. And so, for now, we look at queries of this kind. SQL is more complicated than that, but for now we still stick to the select something from a number of tables where certain conditions. This is the kind of queries we had so far, and you can already do a lot with these queries. And each query of this kind, you can realize it with a combination of these three operations. And on the next slides, you can visualize this or write this down in several ways. And this is before we go to the second part. You can really write it as a sequence. So first do this like a program, then do this, then this. You can write it as a single expression and as a tree. And let's just look at all of them. So let's take 3 tables. You should be familiar with them. That's our movies table. Movies everything has an ID. Title, year, score, the IMDb rating, ID, name, birth date for people, and then roles is who played in which movies. So these are foreign keys referencing these primary keys. And here's a query. And let's look at this if we write it as a sequence of operations. And let's go through this one by one. And already now, maybe you can see there's not one way to turn this into a sequence of operations. There are several ways. We just now pick one of them. The way we define Cartesian product is always between just 2 things. We could have defined Cartesian product as taking variable number of arguments. We didn't do that for simplicity. So here actually I have 3 tables which I have to combine. So let's first do movies and persons together. Now I have all movies combined with all persons and combine that with roles. So this is so now in T2 I have the Cartesian product of 3 tables, right? So this will be huge. That's my table T2. And now in T3 I do the first, actually I do both selects here in the where clause, right? So I have, let me just to clarify what that is here. Let me just write the column names here. So let me in 3, 4, 5, 6, 7. No, this is birth date was 1. I got this wrong. This is just 1, 7. And while I'm writing, you can already look at the sequence and see whether. So this is, this is the column indices in T2, right? When I have the Cartesian product of all 3, I'd first take movies and persons. I just put the columns side by side and then the roles. And now I'm saying R1 is equal to R8. So this ID of the movies table is equal to movie IDs. That's just what's written here. And R5 is equal to R9. This ID is equal to person ID. So that's what I'm saying here. So of this huge table, which contains all combinations of rows from each of the 3 tables, only take those rows where these 2 conditions are satisfied, and that's a select. So now I've realized this. And then it says here, select only, I only want the title and the name. So what do I do here? I take this table from 3, where I've already selected the rows, and I only take columns 2, which is the title, and column 6, which is the name of the person. And I didn't say distinct here, so this means false. So the false here is distinct. So you see, it's simple, nothing really hard here in the individual operations, but when you, I mean, this is not the hardest query, but it already becomes, yeah. You have to think a little bit whether this is correct. So you have to get used to the formalism. Yes, please?
I'm sorry, I'm a little bit confused about D3. You have like R1 equals R8. So you mean that's now like R1 equals R8? Or it's not like we have to set R1 to R8? Because it looks for me like code in Python or something, then it's like you have to set it, but I wasn't sure about if you use like double equal signs or...
Yeah, so this is not code. I think the confusion here, and let me just write it down, this is a function in mathematical notation, and it's saying, I mean, this is a property, right, which maps a row to either true or false, and this is just a mathematical expression which evaluates to true or false. So this is equality, not assignment. Just write it here. Yeah, not assignment. This is not code, this is a mathematical expression on the right? This predicate which we had in the decision of select takes a row and then outputs true or false. Not assignment. But it's good that you ask these questions. I mean, that's exactly the point of the lecture. And you see, it's very typical. You combine very simple things and it quickly becomes not so simple. I mean, this is conceptually simple, but it's already takes some time to get used to it. So look at it a bit longer and please do ask if you have any questions regarding this, or if it's absolutely clear that this implements this query. And while you are still thinking, let me say one more thing. I mean, one could ask why do I even have the distinction? That's also something to realize here. Why do I have a query language and the internal realization of this? This is clear, I think, because that's what the database can now execute, right? You can think about, you will program this is what the exercise sheet is about, and this looks like a program already, right? It's like, first call this function, it computes something, takes two tables, computes another table, then do this, take this table, which I just computed, one of my input tables, compute another table, then do this, then do that. It's basically like a function which the database executes with certain primitives. And so the other question is, well, why don't I specify my query like this? Why do I even have this? And the answer to that is that you probably don't want to write this, right? This is something, okay, it's like the program the database system executes in like a higher level programming language where the primitives are these operations, and this is what you want to say as a user. Maybe you want it even more informal, but yeah, this is for humans, at least for experts, this is for the system. And that's really, yeah, this is what this whole lecture and a lot in databases is about. Given a query, produce this from here to there. And you can imagine that this can become complicated. Any questions before I move on from here or from the chat? So there are 28 people. You should use the occasion to ask questions. And let me just go on. And now I said there are 3 ways to visualize this, and all 3 of them are valuable. That's now a sequence of operation. That's how you would program it. And this is, you can also write this as a single expression. So this is just the same. It's exactly the same as before. My tables, my query. This is just the same. Yeah, it's just what I've written before in a single expression. Think about it. So this is taking this first Cartesian product here. Let me maybe just underline it. It's no, this is not the color I wanted. Look at it and understand that this is really exactly so. This is the first thing I had in my, this was my T1, right? And then I take this as an input and together with this, and then I have this second thing here. That was my table T2, And then I input this as, this becomes the argument of a select something, and this is then the input to this. So it's a sequence. That's the functional approach, right? It's really the exact same thing. And this looks scary, but if you understand it, and I've written it on the slide here, this is no different than if you have an expression like this, right? If you know basic arithmetic, you can add things, you can multiply them, you have parentheses to fix the order of precedence. So if you can do basic arithmetic, this is something where you say, okay, this will take me some time to evaluate, but it will not scare you. It's easy. Yeah, it takes work. 3 plus 4, 7, 7 times 4, 28. It's just the same thing. Yes, please.
Question. So select takes the set and the predicate. So shouldn't there be a closing bracket after the predicate? Because 6 refers to the argument.
So you're saying here, after this, I think so, yeah. And that's probably the hardest part, is writing these expressions correctly. I think you are completely right. And let's, oh my, now I have, and let's just count, right? There should be 1, 2, 3, 4 opening, 1, 2, 3, 4 closing brackets. And this is another. Yeah, thank you very much for paying attention. Correct now? Okay. And then there's a third way, and that's just to do it like a tree. That's just another, it's just the same thing. So I have movies on persons, and then I have Cartesian product. I have another Cartesian product. So just the tree, and the arguments are that's the children in the tree. And let me just show you the equivalent. I think the analogy to arithmetic expressions is really good. Let me just do that. So let me 2 plus 5 times 6. So let's just do that. So this I could show as a tree. So I have a plus here, and I have 2 children. This is the 2, and this is the 5. And actually, if you implement something that evaluates general arithmetic expressions, you will do something like this internally, right? And here I have the multiplications, and here I have 6. And now another question is how you evaluate the tree. If you do it bottom up, it's 2, 5 plus, the result is 7, 7, 6, multiply 42, and so on. Any questions about this? Yes, please.
Is there a reason why these 2 arguments are not as extra leaves like movies and persons, but directly under the select project?
So, you mean these 2 arguments? Why they are not?
Not leaves like movies and persons.
So you are asked, okay, why are these not leaves but in here?
Yes.
Because, that's a good question. They are part of the operation, right? So here, plus and multiplication is really just an operation. It doesn't have a parameter, but these operations are like parameterized. So these are not I wouldn't say these are the input arguments of the operations, these are the parameters of the operation. So some of these operations, the input is always tables, so the tables I put as leaves, and these are the parameters. Does that make sense?
Okay.
So it's just like saying this is a different operation than if I write something else here, then it's like another operation. But they all belong to a class of operations. Yes?
Yes, I have a question about the cross product.
Yes?
And the cross product can get massive big
Oh, yeah.
numbers, so how is it computed in the background?
It's a very good question. So we are still in the early stages, and this looks crazy large. If this is real data, even if it's halfway real, like for the exercise sheet, large, crazy large. And the answer is you will not do it like this. We only do it like this for now. What we will do in the next lecture, we will add additional operations that do something more meaningful. But for now, this is like database theory. We just have these 3. You can do everything, but not very efficiently. In the next lecture, we will add additional operations that do stuff more efficiently. but you will have to wait for the next lecture. So this is building up suspense for the next lecture. Any other question before I continue? Okay, let's go to start with the second part already. So, a single SQL query can have many different sequences of operations. And so I've always just given you one, and this is what we will do now for some time. And just understand that there can be many different sequences and figuring out how to pick the best one. And let's just, and here I've carefully chosen 3 examples. So here is, so I have movies, roles, and persons. So I have 3 tables, and now to come back to your question, this is a query where the only implementation is to compute the cross product. This query is asking for the cross product. We did it in the last lecture. If I ask that to SQLite 3, it will output this huge result. It has to output this huge result. It's not a query you would ask in practice because the result is not very meaningful, but you can ask it. So our Cartesian product is binary. It always takes 2. So we have a number of choices here. So that's 1. Let me first compute the cross product of movies and person, and then take that and compute the cross product with roles. But I could also do it this way. First movies with roles, and then with persons. Now cross product, like multiplication, is commutative and also associative. So I can, there are a number of other combinations. How many combinations are there? How many different query plans? How many different query plans? It's an unrelated question, but... And let me break it down. How many possibilities for the first? So for the first, how many? 3. Why? For the first Cartesian product. Yeah, it's the number of subsets of size 2 of a set of size 3. So it's 3, because I'm leaving 1 out, right? Either I'm leaving persons out, movies, and the order does not matter. So 3 of them, and then the next one is clear. It has to be the other. So it's 3 possible sequences here, how I can do it. Which one would you take? Yes?
So I think the idea is to get the tables small as soon as possible. So if the first thing you do is join 2 large tables, you get a lot of memory. So I guess there are more persons than movies. So you probably should take movies, and probably there are more roles than persons, because a person can play multiple movies. So I guess sequence 1.
Okay, we hear sequence 1, and we heard some thoughts. You didn't hear it on Zoom. By the way, you can also, I hope you are listening and not watching TV show in parallel. Other opinions, which one would you take and why? Yes, please?
Maybe sequence 2 because roles has lesser columns, so maybe that could...
Roles has fewer columns, yeah, so that's sequence 2. So you already see it's not, you all said the right thing. This will cost something to compute it, and you somehow want a thing that's cheaper. But which one is cheaper? Yes?
I think, like, in the second line, the memory usage will be the same, because for the Cartesian product, it's just the amount of elements in the first times the second time. So
Yes.
the order does not play a role in total memory usage.
That's very interesting. So here was the argument: the end result is the same for both sequences, which is very true. The end result is the same. It's always this huge table with all combinations. So T2, what you're basically saying is the second operation here is the same, but the first one is not, right? So T2, this operation, and we will see that, will have the same cost, but I think the first operation won't. So there's still a difference. But you see already with this very simple example, it's not trivial to to say which one is better. Or maybe they're equal. That we heard all the opinions now. First, second, equal. But we do 2 more before the break, then you think about it, and then we do the math. And then I think we're all set for the exercise sheet. So here's another one. And it's always 2. There can be more than 2. Now it's just movies and roles. And Okay. This is somehow not the latest version of the slides, I think. Here it has year, but I can just edit that. So here, and now I just want, this query is maybe not the most meaningful. I'm combining movies and roles, and just those movies with a score greater than 8.0. So I have a cross product here. I'm asking for star. So again, I have to compute it. So I first do the Cartesian product, and then I select those rows where the score is actually greater than or equal to 8.0, or I do it the other way around. First I select those movies, and then do the Cartesian product. Which one is better? Yes?
In this case, it's the second one because the Cartesian product has as argument less elements to combine.
Yeah. So
Elements with the score less than 8.
yeah, so here there was a clear vote for the second one because now I'm reducing the table, right, by selecting movies. And if you know about IMDb score, 8.0 is pretty large, so it will reduce the movies table pretty substantially before I compute the Cartesian product. The roles table is big in both cases, but it does matter whether I multiply it with a small or a big table. And then let's see how that works out. And here's another example, again, movies and roles. And that has another surprise. So now I'm saying from movies and roles, and I just want the title of all movies where the score is greater 8.0. So I just want the movie titles. So one sequence is, let me compute the Cartesian product first. Why not? It's written in the from clause, basically reading the query from left to right. Let me select the movies and then do distinct on this cross product, and I just want 2. And let me just for clarification and just to check whether the indices are. So after I computed the cross product, this is 1, 2, 3, 4, 5, 6. Let's just make sure this is all right, yeah? R4 greater, this is 4. And then I just want the 2 column, and I want 2. So before I show the second sequence, what strikes you about this, yeah?
We don't need roles.
Yeah, we don't need roles. But, I mean, here we have star, right? But here we only have the title, so we really don't need it. I mean, it's written in the query, but the database system can just drop it without affecting correctness, right? So this is I'm claiming, and I hope you agree, that this is also a valid query plan. And you already see this is not easy business. I mean, you can write a lot of crazy stuff in your query, and maybe the system can figure out, I don't need it. But to figure this out, you have to realize that here in the end, what if I drop the distinct? Can I still do it like that?
Then it would be different because the cross product is more like the same title all over again.
Yes, exactly. So if I drop the distinct, this is not a valid query plan. I cannot just take this and put false here, right? Tricky, because this introduces multiplicity. Now I will have, if there are 1 million roles, then each movie will now be multiplied 1 million times. And without the distinct, I now have the title 1 million times. But with the distinct, it doesn't matter. So the engine has to be smart enough to figure out that because of the distinct title, and we will do it after the break. We will see whether SQLite is smart enough to figure this out. Please remind me if I forget it. So I have that in the end. So tricky business, right? And so which one is better? Yeah. So we agreed that this one is correct, but only because of the distinct, and it's also better. So how to tell which one is the best? And this we will do after the break. So let's have a 10-minute break, open the windows, and then think about how to do this. So there was a question about why we can drop this one here for distinct in the chat. I will come back to this towards the end. Maybe can you close the front door for now to evade the party? Okay, so we have seen 3 examples, different possible sequences. There are more than 2 sequences. I always showed a pair only. And now the question is, how do we actually determine which one is better? And you should do something like this for the exercise sheet. So the basic idea is to somehow estimate the cost. Of course, one way is to just execute each sequence, and then you see which one took the most time. But executing them can take a lot of time. So that's, you want to estimate it beforehand and then decide, let me do it this way or that way. So we estimate, and estimating a sequence consists of operations. So how we will do it is we estimate the cost of each operation, and then a sequence is just the sum of the costs of the operations. Then we just pick the sequence with the lowest cost. That's a very simple idea. And we will see that in order to give a good estimate of the cost, I mean, you're computing the cross product of 2 tables. Obviously, the cost depends on how big the tables are. But these tables can again be the result of previous operations, where you only have estimates. So whenever we do estimates, we do not only need an estimate of how expensive is this operation, but also how large will the table be that this operation produces. So estimate is always cost estimate and size estimate. And we will see that the hard part is estimating the number of rows, because the number of columns, you can always tell that beforehand. There's nothing dynamic about that. We only know the input tables from our input tables. Those are fixed, but once we go up in the tree, we don't know anymore how large the intermediate results are. Yeah, that's what I just said. And in real query planning, this is a whole science by itself. You can use much more statistics. For example, what's the multiplicity of the rows? It makes a difference whether some rows can occur twice or 20 times. So let's just do 3 simple cost estimates and then work with them. And this will be super simplistic. It's just to explain the idea. Project is just select columns, right? We have select columns, select rows, Cartesian product. So we have a table, that's our input table, n rows, k columns, and k prime is the number of columns I select. This is not just a number here, but actually which columns. Let's say it's k prime. Here are some simple estimates. Take some time to just appreciate whether it's meaningful or not. So I'm saying the cost is, I'm selecting all rows, so I'm doing something for each row, but from each row I'm only selecting k prime columns. So yeah, if I have a lot of columns and I only select 2 of them, this is only 2. I don't have to do anything. I'm assuming I don't have work dropping columns, but just copying columns over. The result will have the same size, same number of rows as the input, because I'm only selecting columns, and the result will have k prime columns. Yeah, that's our simple estimate here. You can come up with other estimates for the sheet if you want, or you can just work with those. So that's really a difficult science. We are making some assumptions here. So this is what I just said. This makes the assumption that our implemented project is I just go row by row. So I have work for each row, reasonable because I have to copy it, and then I just copy the columns. And so the columns which I don't copy, they don't cause me any work. This is reasonable if the table is stored in row order. If it's really stored row by row, so like a vector, a list of rows. If it's stored in column order, this is maybe not the best estimate, right? Maybe I have a table with 3 columns, and each column is like an object, yeah, in the programming sense. And then instead of copying the whole column, I just copy a pointer. Then it would be a cheaper operation. And this is how a database system might do it. But here we are just assuming we really have to iterate over the rows. So this is just to say that there are some, to have cost estimate, you somehow need to know your system. And cost estimates, it's also something the system will implement. You as a user, it's not something you should typically see unless you are deep into database optimization. It's the simplest one. Let's do the next one. Select. Project is selecting columns. Select is selecting rows. Again, I have my input table. So it's my input table. It's my predicate, which for each row says included or not, right? So I have my input table, n rows, k columns. Well, what do? I go over each row and just see, do I include it or not? So that's a reasonable cost estimate. I have to do work. I have to look at everything, right? Cost is the work I have to do. N over 2. That's the result. What's the result? The result is how many rows were there for which the predicate evaluated to true. And the result will have the same number of columns. Select does not prune columns, only rows. So this is a totally arbitrary estimate, right? I'm just assuming without any particular reason that half of the time this predicate will evaluate to true and half of the time to false. But actually I don't know it. I mean, a better system would just, maybe have a table with 1 million rows, just look at some random rows and check on those rows how often does it evaluate to true or false, and then use that as an estimate. But we're doing no such things here, right? It's just an estimate, it's better than nothing. So I'm assuming it selects something half. Here's another thing. If this is of a particular kind, for example, score greater equals 0, and my table is sorted by score, then I could even compute it, right? One binary search. I see here the scores 8-0 or larger, and then I can even just compute it. So good cost estimates, one can do a lot of simple stuff, clever stuff, and so on. Any questions about this so far? So this is, as I said, this is a whole science, but here we keep it simple. And we will apply this for all the 3 examples in a second. Cartesian product, in a sense, is the simplest because, you just have to compute it. So now you have 2 tables, N1, K1, N2, K2. Well, the result has N1 times N2 rows, and it has K1 plus K2 columns. So you have to construct the whole result. You really have to build it. So that's a reasonable cost estimate. That's huge because it's a product of 3 things. How many rows will it have? That's actually not an estimate. That's exactly the number of rows. You know it. And that's exactly the number of columns. And note, rows is something which I have to estimate, not here, but for the other operations. Columns I always know. There's no uncertainty about the columns. I always know exactly how many columns I will get from an operation. And there's a space missing here, which I've now just entered. Yeah, these are accurate estimates because that's what you just have to for a Cartesian product. And this has come up several times now already. Well, does the system really do it? Well, if the query asks for it, you have to do it, but typically you can avoid this. And the whole next lecture is about avoiding Cartesian products as much as possible. Now let's apply those, and this is also something you will have to do for the exercise. So here's our table, and here's our query. And let's just write on the side our, let's do this slowly. So this is a table, let me just say this is N1 times, and the K1 I actually know, it's 4. Let me just always write it like this, rows, X, columns. Yeah, it's always table, it's always 2-dimension. This one is N2, number of rows, depends on the input, times 3. It always has 3 columns. And this is N3 times 2 columns. Okay, sequence 1. Now let's do the... So the T1 table has... Okay, what's the cost estimate? Cost What's the cost estimate for this Cartesian product movies person? Given what we just had. You can also write it in the chat. Cartesian product, it's n1 times 4, n2 times, n1 times n2 times 4 plus 3. I agree. So it's n1 times n2, and let's just write it as it, so it's 4 plus 3, so 7, right? That's the cost estimate. What's the rows? What's the estimate for the number of rows? Yeah? 4 times 3? Number of rows? Yeah?
Only n1 times n2.
N1 times n2, yes. N1 times n2, that's the number of rows, and the columns is, actually we always know that exactly. How many columns will it have? 7, yeah, 4 times. 4 plus 3 equals to 7. So this is more of an attention exercise, right? So, but you have to do it. And so let's, so now we have T1 times, so now we are already working with the estimates. But let's do that. So the cost of this one is now, what is it? And you can write it in the chat or... So now one input table is T1, right? And this is, we now need to work with the size estimate for T1. So what's the cost? Yeah?
So the rows of the first table is n1 times n2
Mm-hmm.
times n3 for the second table, and then times, in brackets, 7 plus 2.
Mm-hmm. Yeah, and let's immediately write 9 because we know the exactly rows. Somebody else? What's the estimate? And actually we can, let me even write it here because for a Cartesian product we just know it, right? Number of rows is just n1 times n2 times n3, right? And columns is, yeah, it's also clear, it's 9. Okay, now let's do the same thing here and maybe a little bit faster. Just to cost. So what's the cost of this one? You can just say it. Maybe somebody else. You can just say it. M, so there's in the chat it's M, M1, M2. Yeah?
It's n1
N1 times
times 6.
N3 times 6. Yeah, it's these two, 6. Okay. And is the door in the back, is it open or closed? Closed. Maybe you can open it so the CO2 levels are rising because you are thinking. Okay, let's, we have to do 2 more. So the number of rows is just N1 times N3. And the number of columns is just 6. And this is, without much thinking, what's the result for the second one?
The same, like 2 units equals 1.
Yeah, it's the same. That's what we already realized, yeah? Exactly the same. Same as above. We don't even have to do it. Same as above. So now, so essentially to figure out which one is better, we have to, so what's the, we essentially have to compare, and let me just do the 7, let me just write 7 here, times 7. And so what will be, what can you say about the size of these 3 tables, about N1, N2 and N3? Yes?
I just want to say, if we
Yeah, exactly. We need to know something about the size of the tables. Let's ignore number of columns. Just looking at N1, N2, N3. What can you say with some certainty? Which, without knowing too much about. Yeah?
I would argue that N1 is smaller than N2 and N2 is smaller than N3.
Yeah? N1 and 2 maybe one can, but what can you say with certainty? Which one is the largest here and why? Yeah? Yeah, Rolls is the largest. Why is it the largest? Yeah. I mean, each movie has a lot of actors, right? And an actor usually plays in a lot of movies. So we expect, yes?
Not necessarily.
Yeah, of course, there are always worst case, but in a real data set, that's what we expect, right? So let me just write that down. So let me just write it as reasonable assumption. And while I'm writing, think about it. Anything on that slide? So reasonable assumption is that both N1 and N2 are much smaller than N3, right? Because, a movie has many actors. Not every movie, I mean, there may be movies with just one actors, and an actor plays in many movies on average. Plays in many movies. So the roles tables will be okay. So, what can we say? So we can say that, and given that, which of the two, under that assumption, which of the two sequences is better? Yeah? The first, yeah, because N2 is much smaller. Yeah, so let me just put that here. Better. Because 7 times N1 times N2 is much smaller than 6 times N1 N3, because there's the roles table, right? So now we have it, and the second part is basically the same. Okay, let's do it once more. And maybe we can open that door as well. CO2 levels are rising quickly. So that's the one where we have this stupid cross product, but we can't get rid of it because we have a star here. So let's be faster now. We can reuse a lot of the stuff we have seen here. So this is now N1 times 4. This is now our second table, N2 times 2. And again, N1 will be much smaller than N2. So let's just do so what do we have here? Cost. You just tell me what's the cost of this one. You can just say it. Yeah? N1 times N2 times 6. That's correct. Number of rows. We know it exactly, right? It's a cross product. It's N1, N2. Number of columns is 6. And let's do this one. What's the cost estimate? And remember, for a select, that's a select rows thing. We just assumed that half of the rows are selected. So what's the, yeah?
Should be the same, and 1 times 2 times 6.
Cost should be the same? Yeah, exactly. We said selecting rows, you have to go over the whole table. So you can check, I mean, the slides are online. What's rows? That's now a cost estimate, yeah?
Well, it depends on if we know that 8 is a high score, but if we don't,
But our cost, we are working with particular cost,
then
yeah?
2 times
You are absolutely right. Thank you for paying attention. That's why we're taking it slowly. Number of rows with our cost estimate?
So we said that about half gets it gets true by the predicate, so half N1, 2.
Yeah, half N1, N2, and columns is not an estimate, but we need it for the cost, and this is just it's just 6, right? Doesn't change. It's a star, so we have all 6. Okay, and let's do it. The cost is also wrong.
In the slide, at least, it says n times k.
Yeah, you're right. So it should be 6, right?
Yes.
Yes. Thank you for paying attention. So you see, it's really an attention thing, yes. So let's do this one now. And you have to, so there's always intuition, and now let's do this one. So cost of this one. What's the cost? You can just say it.
N times 4,
N what? N1 or
times 4.
N1 times 4. N1 times 4 rows. Yeah, we're assuming that it's, and columns is 4, right? Cols is 4. And now let's take this operation, which takes this one as input. What's
1.5 times N2 times 4 plus 2, 6.
So it's this input, which is just our assumption, times N2 times the combined rows, right? Times 6. Yes, think so. Rows. What's the row estimate? It's difficult. Somebody else maybe? What's the estimated number of rows? So now I need the estimate for rows of T1, and for rows I know it. Chat? Or somebody here, except it's typical exam task, so you will have to train for this a little bit. It's a focusing thing.
So we know the amount of rows from T1 is N1 half, is N1 half times the amount of rows times N2.
Yes, so it's N1 times N2 divided by 2, right? I just reorder a little bit. Yes, and calls, this is, there's nothing to estimate, that's 6. Okay, and so let's just write the total. So what do we have here? So total. The total cost is, what's the total cost of the first sequence? It's just the sums of the costs of the individual operations. Yeah, it's 12 times N1, N2, right? What's the total here? So that's 3 times N1, N2, right? Plus 4 times N1. Which one is better? Yeah? Yeah, the second one is better because, yeah, this N1, even no matter what this N1 is, you could just estimate it by 7 N1, N2, but actually it's much smaller. So yeah, better. So yeah, you get a feeling about this, but you can imagine if this is more complex, you actually have to do the math, and that's what the database engine will do. So you can already see in a nutshell what the engine has to do. Maybe it has 15 different sequences. We'll just compute the cost for each and just pick the cheapest one. And a totally different question is how you do that efficiently. Do you actually generate all plans, evaluate all of them? This is what we will do in lecture 6. And let's do one more. And this is the last one. And then I have some comments. We will look a little bit more into SQLite and some comments about the exercise sheet. But let's do that. That's the funny one, and now we'll come back to this distinct thing. I mean, we can do it even faster now, but so this is n1 times 4. This is n2 times 2, and again there will be many more rows. So n1 is much smaller than n2 for a real table. The rows table has many more rows, fewer columns. So that's our one sequence. And let's just, so for now we should be fast. That's movies and roles. That's the first operation is always easy. Actually, if you get used to it, they are all easy, but just have to get used to it. The number of rows is just n1 times n2. Did I pick the wrong? This is so mean. I have to do that again. It's still off here. It's just to challenge me. I have to click somewhere else than where I draw. It's the last example, so bear with me. n1, n2 times 6. I will do it a little bit faster now. n1, n2, number of columns is 6. And this one is actually an equality, so for the Cartesian product, we always know it exactly. The second operation is cost. So now it gets the T1 as input. We just do as if this would be our input. N1, N2 for select. We just iterate over it.
You missed the times 6.
No, I don't. Oh yes, no, it's the. Oh yes, you are right. It's okay. The rows is, I'm just assuming and this is an estimate that I'm selecting half of the rows totally arbitrarily. Nothing changes in the number of columns. And now I have this one. And what's this doing? Now I'm just copying one column. I'm not having a cost estimate for the distinct. I just act as if the distinct was for free. So what do I have here? I have one column and n1, n2 over 2. So I think it's just this one, right? It's the number of rows times 1, because I just select one column. And this is now selection of columns, so number of rows does not change. So that's n1, n2 over 2. And the number of columns is of T3, yes? 1. It's just selecting one column. Okay. And now let's do this last sequence. And then I will cost. What's the cost? One more time, yes? And 1 times 4, that's correct. Rows, I'm assuming that I'm selecting half. Columns is 4. And now this operation that's now, I'm just taking the number of rows n1 over 2, and hope that's correct. The number of rows does not change. This could even be an equality sign. And the number of columns is 1. Now let's look at the totals, sum it up. It's our last example. So total is, what's the total here? That's actually a nice, what's the total for sequence 1? It's hard work. What is it? It can be compressed into, yes? 12.5 and 1 and 2. Yes? And the total here is, what's the total here? Yeah? 4.5 and 1. Yeah. And I think even without any assumptions, it's pretty clear which one. Yeah? It's a mistake?
You
Yeah.
It could be equal, but it couldn't because of the distinction, right?
The rows could be equal. What's the?
In the last estimate,
Yeah.
the rows of the projection has to be approximate because the.
Oh yeah, absolutely. So this is, I think, what you are. Yeah, this is just an estimate, and this actually this should be a.
Only if it's not distinct.
Yeah, this is not. If distinct is true, this is not necessarily correct, right? And now I have to find the right. Oh my. This is your comment, right?
Yes.
Yes, it's correct. So yeah, if it's distinct, it could be less. If it's not distinct,
There's also a mistake on the next slide.
what do you mean on the next one? Here on the next one. You're not talking about the future, but the past relative to which one?
In the next slide.
This one?
The calls are exactly K.
It's a good point. Yeah, I didn't make that distinction earlier, but I just realized that it's a good distinction to make. What do you actually know and what don't you know? There's no equal sign here. Where's the equal sign? Here it is. Okay, thank you very much. Let's go back to the... So this is 4.5 N1, and if you do it that way, then it's super clear, right? I mean, this is not only the factor is smaller, but here you have the whole product, which is gone. And now we will come back. So this is clearly better. So the hunch we had. And now let's have some more fun with SQLite and talk a little bit about the exercise sheet, and then we are done. And I deliberately, compared to last year, removed a lot of material from this lecture so that this becomes clear. And then we move joins and everything to the next lecture. So let's look at SQLite 3 now. SQLite 3 or any database system will also do something like this. You get your query, and internally it does something like this. And now let's just look at this. And actually you can look at it by saying, just have the query and then say explain query plan. You can just, so SQL has this tradition of just you write it like you would say it. Explain query plan, and actually there are two things. Explain query plan. Query plan is what we have seen. This is a query plan, right? Which you can show either like this as one big function or as a tree. It's called a query plan. It's a plan how to execute the thing. You can also say just explain, which gives you something different, and we will see all that. Just one general comment. SQL is pretty standardized, also not 100% standardized. There are dialects, and certain systems have some fancy operations which others don't, but this, what you see here, select from where, this is 100% standardized. The output of this explain thing totally depends on the system. So every system will do something else, and we will now have a look. Yes?
Is there some government body behind this?
Is there some government? Government is probably not the right name, but there's a standardization committee. And the weird thing about SQL is the SQL standard, if you want to read it, you have to pay for it. And it's really expensive. And it's a document with thousands of pages, so if you want, you have to pay for it, and it's expensive. But of course, if you just want certain information, you find it everywhere. But you really want all the details, you have to pay for it. Which is weird. It's not the case for C++, for example, but the SQL standard. And it's huge. We are just looking at the core here. Let's just do this now, because it's interesting. And let me use the occasion to introduce the exercise sheet to you, which is really nice, and I've already said it and will say it again. Please do it. So exercise 1 is implement these 3 operations: project, select, Cartesian product. Next slide is a few more explanations about that. And there's this big TS, it's now bigger movies data set, and I've downloaded it for you now already here. So it's this movies tables tar GZ, and if you unzip it, then you get several TSV files, the awards, names of the awards, the movies, the persons. This should look all familiar to you. So this is when you unpack what we have here. So that's the movies. Movies, title, year, description. You have more information which you don't necessarily need or not need at all, but doesn't harm if it's there. So let's just look at maybe one more, award names. Yeah, this is the award ID and then the name of the award. It's in a separate table because you always want IDs separated from names. By the way, just so you know, the query on the exercise sheet asks for Oscars. The Oscars, yeah, that's this biggest movie award, and the official name of an Oscar is Academy Award, right? It's not, you don't find Oscar in here. So that's the Oscar for Best Picture, Oscar for Best Actor, Best Director, Best Actress. Yeah, this is the Oscar for Best Actress. You will find this out. Okay. These are the tables. So let's do a little more SQL. And actually we have prepared a lot of stuff for you. So just all this basic stuff, we do it for you. It will take some time to get acquainted with it. So this query SQL, we also give it to you. This is something you have already learned for the last exercise sheet. Just say separator is tabulator. It will just import these tables. So we did that for you. And here it will actually execute a query for you. This is not relevant for the exercise sheet. It's just an example so that you... it's actually the query from the exercise sheet. Let me just show you that query. This is the query. It's actors who won an Oscar, any Oscar for a movie from this millennium. This millennium is started in the year 2000 for a movie with a rating of at least 8.0, and I want the actor, the movie, the role played, and which Oscar. There are many Oscars. And your task for the exercise sheet is to write your own database engine which computes this, right? This is a really interesting exercise. And let me also say that again, the exercise sheet afterwards will build on this one. So if you want to follow us here, you should do this, otherwise you can't do the next one. So, and this is the SQLite, the SQL query. So it's not part of the exercise to do that. We came up with that for you. And let's just execute it that's very simple. I hope you remember it. You just pipe this into SQLite 3. And I'm not even using a database file because these are not huge files. Let's just do it. Yeah, this worked just fine. What did I do wrong? Echo. Yeah, echo is just a cat. So I just piped this into... yeah, and I think I should make this a little larger. Why this is... maybe I should make the font... why is this showing... Do we know why it's showing new lines here? I'm not sure. Not sure what I did wrong. It's the result table. Oh, there is funny stuff going on here. Let's see whether we can fix this for the display. It's because of this 70 here, right? Actually, there's a dot width where you can say how large you want to make the table. Let's just play around with it. Yeah, so this is 4 columns here. I'm saying use 23 characters, 17. It's just for fancy output. Let me just try it one more time. Okay. Okay, let me do a trick cut. I'm a professional, so let me just do it. Yeah, that's a nice one. Okay, I just did cut minus the first 100. So that's just, I loaded and that's the query from the exercise sheet, if you give it to SQLite 3. So it's just a movie where you have an actor. So here it's Heath Ledger. He won an Oscar for Best Supporting Actor. You can imagine it here. And the role was the Joker and the movie was The Dark Knight. And this is, yeah, it's popular movies score 8.0 or higher. So this is your query for the exercise sheet. And now, let's look at something simpler. So again, I just import this and let's do this first. From movies. Yeah. And let's play around a little bit with this so that you understand the explain. So 5 more minutes and we're done. I don't need any width now, I think. Yeah, so that's just a simple query. What will it do? It will just... Actually, let me do the following. I think it makes more sense that way. I'm just reading these import statements, and let me move that from demo SQL to import SQL, and now I should be able to import SQLite 3 and just put it in a, right? So now it's in my movies DB, and now I should be able to, let's just check that. I forgot something?
The 3 after SQL.
Yeah. Thank you. And now it's persisted in a database file, and now let's just do from movies limit 10. Now I should just get the 10. Okay, that's too much information. Maybe title, year, and IMDb score. Yeah. And now I don't have fancy, yeah? That's the... So this is just title, year, IMDb scores for the first 10 movies. And now let's just do explain. That was the second. I can just write explain before this, and now, okay, that's what SQLite gives me. So explain now tells you on a low level what the database is actually doing. We will not go into this, but feel free to look at it for the exercise sheet. This is now super low level. It's not totally unstandardized. So what you have here, P1, P2, P3, it's something like cursors in the table. So it's like I'm now at this table in the so-and-so many rows and so on. And so you have stuff like rewind, which sounds like from the last millennium, and it is. So it's like go back again over the table. You need stuff like this. I'm not rewind, you only have it once here. So this is low-level stuff now. And why do you have 4 of them? We don't go into this. But this is what you get with explain. Explain gives you on a very low level what the database system is doing.
Indentation of column 4 to 8 have a meaning?
Yes, it absolutely has a meaning. So this is like nested loops. You have a lot of nested stuff if you combined 2 tables. I mean, we can... Yeah, I have 3 tables here, right? But I have 2 tables here. Maybe, I mean, look into this yourself. Movies, comma, what else did we have? Persons? Oh, I'm not sure. Oh, yeah. Yeah, you see? Now I have a join of 2 things, and now it's doing, now you see the nesting here. That's 2 nested loops, basically. But this is not what we're going into today, but let's do the explain query plan. Now you get something more like what we have seen. This is now just title, year, IMDb score from movies, first 10. Yeah, okay, that's now so it just says scan movies. So it's kind of, yeah, but the limit is not even here, but it says scan movies. And now let's look at this query, at this last query, and see whether, so let's just take this one. It should work. Maybe it's, let's just try this. Query plan, select distinct, title, from, and now I'm doing movies. How is it called, Robin? Is it called roles or our table, or? Roles, so it is actually roles. Title from roles where, but I think it's called IMDb score, right? IMDb underscore score greater equal to 8.0. I think that's the query. Yeah, it's movies roles, distinct title, and that's the one where let's see what the, okay. Okay, it does say scan roles, so it doesn't look like it optimized it away, right? That's interesting. It wasn't smart enough. We don't go into this, but it's fun to show it at least. Okay, this looks like it doesn't do the smart thing, if you ask me. The fact that here it says scan roles when actually you don't have to, right? Yeah?
Why does the projection not appear in the query plan?
As I said, why does the projection not appear? It's not standardized what the system does. It would be nice if the system does what I teach in this lecture, but Richard Hipp did not ask me. So it's up to the system to show something here. Here you are basically just seeing what I'm doing with the tables. Play around with it yourself with more complex tables and you will see what it does. This is super low level, this is a bit too high level. It would be nice to have an intermediate representation, but this is not standardized. And you see it's not doing the smart thing, right? So if I don't put the roles here, and to explain query plan, now I expect to not see now it's just scan movies, and it's mentioning something like B-tree, which we will talk about later. Okay. And now back to this question. Oh, here it says the C++ standard also costs money. Okay, and the SQL standard is more expensive. It's 9 books, where each of them costs $250, and the C++ standards just cost 221 Swiss francs. Okay. Once more, we are almost done, and maybe you can close the door once more. It's just a few more minutes. Please ask if it's not clear, because there was the question in the chat, why? Because of the distinct. I will just explain it one more time. Because of the distinct, you don't need the roles. If you have a distinct here, you really just want a distinct title from movies. And if you have the cross-product multiplication with roles, what it will do is it will multiply each movie with how many roles there are. If there are 1 million roles, you have each movie now 1 million times. And with a distinct, these duplicates will be eliminated again, because it's just the distinct titles. I could just remove the roles and have the same result. Without the distinct, the correct answer will repeat the title 1 million times. It's a subtlety, but it actually tests whether you have understood the semantics. So without the distinct, this would not be correct. And we just saw that SQLite 3 is not doing anything clever. And that's actually pretty deep. That's also why I showed this. SQLite 3 does the basics, what it does. It's very, very basic. Richard Hipp did not attend such a lecture here. He's basically self-taught, but all these little low-level details he did super well, but beyond that there's nothing fancy in SQLite. It does not even do this optimization, and there are 10 other obvious optimizations which it doesn't do. But like the simple stuff, it does really super fast. And that's why it's so popular. And so it's interesting that this is the most popular database, not using fancy algorithms at all. Last slide. Please do this exercise sheet. This sheet is about implementing what you have learned today. So what you have learned it with examples and the abstract things. So you will see implementing a project, selecting columns, selecting rows. This will be easy. It's 2-3 lines of code. But understanding how you build an engine from this, right? You now have to, you have this tree thing, you have to traverse the tree or whatever. I'm not showing this to you now, but you will see in the code template that each operation is a whole class, right? Let me just show it to you once more. I mean, you have to implement something like this here, right? And what you will essentially do, what you will see when you do the exercise, you will essentially write this in code, stuff like this, right? You don't do the query planning. Your system does not figure out what the best sequence is, but you write something like this in code, and then your code is such that it will execute this. And you will see that each operation is not just a single function, but a whole class, And these class objects implicitly form a tree. And my point is, I'm not explaining it here. To understand this, you have to do it, right? This is not something I can explain here, right? You have to do it, and it will take some time, and please do ask questions in the forum. If you don't do it now, you will have to do it when you prepare for the exams, otherwise you won't understand it. So better do it now when you get feedback from your tutors and everything. And as I said, exercise sheet 5 will build on this. So this is a strong recommendation to do this exercise sheet. And it's a lot of fun. Afterwards, you have a simple database engine written by yourself that works. Any questions? No questions. So have fun working on the sheet and see you next week. Bye-bye.